I'm going to talk about neuron depolarization. Depolarization is one of the most important processes in the brain. It's the main process that causes the cascading effect of neuronal activation. The biological models we have perfectly captures this behavior of the brain this way, and the computational models used across the board in AI also reflect this spiking and fire in action. We have the earliest example of the spike and fire action in the McCullough-Pitts neuron 80 years ago, a very famous paper, and one of their rules they put forward as accompanying their computational model of a neuron was that a neuron can only spike or fire, aka all or nothing response. So if we think about this, all or nothing meaning either you reach a threshold and you go as far as you can after that threshold, or you don't reach the threshold and nothing happens. That's all or nothing. This is true for biological neurons as well. So if we imagine a neuron, we have the cell body, we have dendrites coming in, the spines and everything possible, integrated in the cell body and outputting in an axon to another dendritic spine, etc. But the dendrites is what we're focusing on. Each dendrite receives a flow of ions if the output of another neuron is connected to these dendrites is excitatory, and ion flow occurs. We see this in the other video called axonic transmission, where you have the neurotransmitter across the synapse gap. If it's GABA, for example, it would be an inhibitory neurotransmitter. If it's glutamate, it would be excitatory. Whatever it is, if it's occurring to a dendritic channel, then it will be a graded potential. Stuff to research if you don't know, but I'll probably make a video on it, involving saltatory induction and myelin sheaths, etc. But for now, the summation of the inputs from the dendrites depends or decides whether the neuron will fire or not. So let's say enough ions come in, excitatory ions come in from the dendrites to cause a all or nothing response. What threshold might we think that is? Probably not too far from the normal threshold, the normal resting state of the neuron. That would be pretty sensitive if you think about it. So the resting potential of a neuron is actually about minus 70 millivolts, and it looks something like this. Of course, the intricacies we are avoiding for simplicity's sake. The threshold we're talking about is minus 55 millivolts, give or take, and we represent that as a dotted line to show that anything that reaches minus 55 will immediately cause an all or nothing response. So we have our inputs causing a minus 55 response. What happens over here for the threshold to become a cascading reaction and an action potential? We get two gates that open here in the membrane. We get the sodium gate, voltage gated ion channel. We get the potassium gate, voltage gated as well. These both open at the threshold at the same time. However, sodium is much faster to open and to close. Potassium is slow, and it doesn't open right away. It actually opens somewhere down here, but we'll get to that in a second. Now you'd think that because of these two gates opening, that we'd face a difference in the intracellular charge, where we were originally at minus 70, now we're at minus 55 millivolts. And if you thought that, then you are right, because we see two positive ions here. We have a negative intracellular charge, therefore we're going to move towards a more positive state. And over here we'd write the first milestone that would logically we would consider, which is 0 millivolts. Now nothing special happens at 0 millivolts. You would expect in a computational model, maybe if you were just doing this for the first time, that we would have a binary stop at 0, like the threshold is finished or the duration of the change is finished at 0. Because we're dealing with a physical and a biological process, it's not quite as perfect as you'd want it maybe to be. But there's a very, very interesting and very, very powerful effect that happens when we bound past 0. We'll observe that now. So between minus 30, plus 30, and plus 40 millivolts, we reach the peak of this ascent into a repolarized state, or depolarized state. And at this peak, the Na plus sodium channel, which is currently flooding the cell with sodium, and the K plus sodium channel, which is still slow, but it started to fill the intracellular environment with sodium. This sodium one, it instantly inactivates at this place. When it inactivates, the lid for it, you can say conceptual lid, closes straight away, and Na plus completely stops flowing into the ion, into the neuron. After that, the driving force for the K plus channel is minimal, because we already have a positive charge inside, we have a positive charge coming in. So in fact the outflow begins, or the efflux begins of the positive charge. And this is the depolarization stage, repolarization stage, sorry, and it's what we call the relative refractory period. If we were to draw a graph of how it would look, it would certainly look something like this. So if we had the resting potential of minus 70 millivolts, climbing to a threshold of minus 55, going all the way, crossing 0 about there, and then a plus 30 to plus 40 over here. This entire sort of place, we are experiencing an action potential. When we return on the descent, due to the Na plus ion channel closing up here, and the K plus leaking out of the neuron, we start to go beyond the initial resting potential, and we reach quite far. We reach about 80, minus 80 to minus 90 millivolts at the trough. right there. And this period is quite special, so we'll mark it out for now. This is the relative refractory period, after which we return to a resting potential. So once we enter the action potential, consider that maybe we get another signal from the dendrite, almost instantaneously, which is a very strong stimulus. Why can't we just collate those two signals and go up to 100 and minus, or like plus 60 or plus 80 millivolts, so just multiply it by 2. It's because at this point there are no more Na plus ion channels to open, there's no more K plus channels to open. Everything is currently rushing in, and by physics you can't make it rush in any faster. So in this entire period, which is called the absolute refractory period, we cannot experience another action potential at all, no matter what you do. But then we have the relative refractory period, in which if you experience a strong enough stimulus, like a really strong stimulus, that overcomes the difference at minus 80 to minus 90 millivolts, then it will offer another action potential for sure. And on the offshoot, it won't, like, go further like that and start an infinite loop of going further. No, it will stay at the same sort of trough and allow you another relative refractory period. If we refer to long-term potentiation and depression, we can find a link there. I will explain it here, but once we reach the hold on. Some things to consider during when thinking about the equilibrium of the resting potential is that during the state of both returning and maintaining the resting potential, returning to and maintaining, we have two special processes that occur continuously without stopping constantly. One of them is the potassium leak channel, which is always open and works from osmotic pressure. It's a passive conduction system and it doesn't require an active transport. The other process does require active transport. It's the sodium-potassium ion pump. Pump meaning it works, right? It needs mitochondria around it. But that pump removes 3 sodium ions from the intracellular environment and inserts 2 potassium ions. So in this way, over the long term, the potassium content inside the neuron is maintained and the sodium content inside the neuron is removed suitably. So if you think about potassium exiting and sodium, we never mentioned sodium exiting, there has to be some sort of balancer, and the K plus Na plus pump is the balancer in this equation. This wasn't the best explanation, but it is for sure a general concept of how this works. For further reading, myelination, highly suggest. From there you can learn about the difference between an action potential and which we just discussed, and a graded potential. So, for brief insight, the action potential will actually continue the action potential, imagining this as an axon, it will continue with a constant surge. It's not connected to this graph. it will continue with a constant surge like this. If you measure along any point in the axon, it will be constant, right? So this means myelin exists here, and between the myelin we have certain structures which allow it to maintain amplitude across the axon. If it's a meter-long axon, this is remarkable. It's hard to even have a wire in real life that maintains signal without an external influence. But a graded potential adheres to what we know, which is it will be a spike like this at the start of the axon, and then essentially we can't measure every point of the axon, but it will form a graph like that. Graded potential, meaning if you measure here, 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 this will be true. And it won't exactly die off, because a dendrite, if it's that far away, it will still have an input. But if it's closer, maybe this close, if its spine exists right here, it's really close to the soma, then maybe it will have a larger effect. It will be right here. That is depolarization, the basics, and an insight into myelination, gradient potential versus action potential.